elasto-capillary deformation of elasto-capillary deformation of thin hydrogel sheet that can be used as the tool to characterize the mechanical property of hydrogel and used as means to build the assembled structure through the capillary interactions. I'm just going to use the laser pointer to make sure. Okay, good. So what is capillary interaction? So here we are particularly interested in lateral capillary forces. So let's say you have several thumbtacks and put them carefully on the water surface. Then what you will see? So the pins begin to clump together. So capillary interactions arise when the distortion of fluid interface created by neighboring particles overlap and the particle approach each other to minimize the total energy. So here are three different cases: the capillary attractions between negative monopoles and between positive monopole, and capillary repulsion between a positive and a negative monopole. This happened due to the particle weight and buoyancy. However, in the absence of external forces such as buoyancy and torques, the wettability and shape of particle decide the local deformation of fluid meniscus, that giving rise to long-range interparticle interactions laterally. For example, 2005 Azenute group showed a side-side versus end-to-end particle attraction depending on the surface wettability of ellipsoid. And 2009, this Debye group reported geometry effects. So they varied the aspect ratio of an isotropic particle to form the different alignments, either curved surface to curved or flat side to flat side. So previously, the focus of capillary assembly has been on assembling rigid particle. Our work was initiated by a question of how about using soft objects, for instance, hydrogel microparticle, that can potentially change their shape reversibly by external stimuli and can be designed to various shapes. So then what hydrogel we will use and what characteristic will be utilized. Through this talk, when I say hydrogel or polynipan, pnipan, that specifically represent the temperature responsive for crosslinkable copolymer, pnipan random copolymer, that consists of temperature responsive anisopropyl acrylamide, acrylamidobenzophenone for photo-crosslinking, and acrylic acid for enhancing hydrophilicity, and rhodamine B for fluorescent imaging and visualization. The principle of temperature responsive actuation is originated from lower critical solution temperature, LCST, behavior of polynipan. In other words, when the temperature is lower than LCST, the polymer chains swell and expand, and the higher than LCST, the polynipan chains transform into globule conformation, so which is collapse due to the hydrophobic interaction, therefore deswell. Also possible to globule to coil transition reversibly. So this property gives the reversible shape reconfiguration of this material system. Okay, then what characteristics of this material system allow us to program and generate various 3D shape from the 2D flat state of NIPAM. The fact that a degree of swelling ratio can be determined by UV dose during photo-crosslinking process. So lower UV dose form the lower crosslinking density of network, whereas higher UV dose makes a highly crossing polymer network, therefore lower swelling ratio. So here is a simple example to show the shape programming concept. So the outer region has a higher crosslinking density than the center rectangular area. So you can see that slightly darker color. So this non-uniform crosslinking density leads in non-uniform growth by swelling. Therefore, it forms a curved 3D shape. So the binary patterning of single material pnipan material allows us to prove the concept by assuming modulus difference of hydrogel is proportional to inverse of swelling ratio difference. However, once we start to consider multilinear patterning to create more complex structure, or need to integrate other material that has a different mechanical property, then we should know what is accurate value of modulus in order to program or predict the shape transformation. So although there are different characterization techniques for measuring elastic modulus of polymer material at small scale, such as nano-indentation and micropipette aspiration technique. However, measuring the modulus of micron-sized, very thin, soft sheet or hydrogel sheet still remains challenging. The motivation of this work was basically how we directly measure and quantitatively measure the modulus of micron-sized, very thin hydrogel sheet. I'm talking about tens micron thick, without supporting layer in swelled state, hydrated state, and aqueous media. So our idea was utilizing the balance between the surface energy and bending energy. This balance can be described by elasto-capillary bending length, LEC. In given material system, which is NIPAM, the characteristic dimension R of hydrogel sheet is to be similar order or slightly larger than LEC. It means that the fluid surface energy can effectively compete with the bending energy of hydrogel sheet. In 2007, Pai and co-worker reported capillary bending at liquid air interface. So here they built the 3D structure by wrapping a liquid droplet by an elastic sheet. So they claim that the minimum in-plane length, which is side length of sheet for wrapping a droplet, which is called L critical, is determined by elasto-capillary length as well as geometry-dependent prefactor. So based on our simple calculation of LEC that I explained in the previous slide, this principle can be used as a promising approach to measure the elasticity of thin hydrogel sheet. Then what should do first? So first we should verify this physical principle, specifically geometry prefactor A in different material system, as well as for liquid-liquid interface, because we want to test hydrogel in swell condition. Moreover, effect of liquid contact angle on polymer film should be clarified. In the light of this concern, the commercially available Kapton film, polyimide film, was used because it has excellent chemical resistance and its mechanical properties are well characterized. So therefore, it allows to test several pairs of droplet and continuous liquid phases for varying the contact angle and surface tension. For example, you can see the yellow Kapton film that is nicely confined at interface of silicone oil and aqueous solution. So by reducing volume of liquid drop, the Kapton film showed the two different bending behavior depending on the in-plane size, L. So L is longer than L critical. The film was able to bend until encapsulating droplet completely. Otherwise, the surface tension was not sufficient to bend the Kapton film. So three-phase contact line depinned and film gradually reopened. By doing a series of this calibration, the prefactor A were calculated from the L critical for square and triangular shapes of Kapton film. And this results clearly indicate that prefactor A doesn't depend on contact angle of droplet. Also, our experimental prefactor values were in good agreement with the literature values. Okay, so we verified this physical principle. So now we are ready to measure the hydrogel modulus. So we prepared the polynipam thin film by drop casting polymer solution onto sacrificial layer and do mask-assisted photo patterning. Then crossing gel sheet with desired in-plane size and shape, then detach from the substrate by dissolving the sacrificial layer. So this is micron scale. So using the Kapton film that is a millimeter scale, we was able to manually perform the experiment. But for a micron-sized hydrogel sheet, the liquid drop suction was conducted by tapered capillary glass microcapillary, where the opening diameter is only about 10 to 15 micrometer. The plane strain modulus E bar of hydrogel can be directly estimated by L critical from the elasto-capillary bending experiment. So here, the fully swelled hydrogel sheet has place at perfluorooctane and aqueous solution interface, as shown here. When the in-plane dimension is larger than L critical, then gel sheet can completely encapsulate the droplet by reducing droplet volume. Otherwise, gel sheet is reopened by deepening of a liquid contact line as shown in this video. So you can see that the film cannot encapsulate. So we directly get the L critical by varying the in-plane dimension L in the experiment. Therefore, the hydrogen modulus with the different swelling ratio, so here volumetric swelling ratio Q, were characterized by experimentally obtained L critical. So using that data to further understand that how modulus and swelling ratio of hydrogel depends on crosslinking. So we use UV-based spectrometer to characterize how the conversion P of benzophenone unit increase as a function of UV dose. So here the plane strain modulus E bar value obtained using elasto-capillary bending method that we developed it. Okay, so the relationship between Q and P here reveals a linear dependence in log scale and best fit power law of -1.6. So this is in good agreement with the theoretically predicted exponent of -1.5. And the measured E bar as a function of P reveals a best fit exponent of 1.7. Then you can see this correlation. We got the exponent of B over A is equal to -1.1 from our measurements. The prediction of shear modulus G is proportional to Q to the -1. It has been verified in theoretical model and several previous reports. And you can see that our result is in pretty good agreement with the predicted power law here. Also, it means that it proves that elasto-capillary bending method can give a good estimation of hydrogen modulus. So now we know exact value of modulus of P95 hydrogel. I took an advantage of comparable energy scale between capillarity of fluid and elasticity of microgel sheet to measure the modulus. So we use the liquid droplet. But let's think about if the flat fluid surface interact with the hydrogel sheet, what would happen? So we determine the two-dimensionless number to understand surface tension-induced hydrogel deformation. So first is elasto-capillary bending number C sub B represent the ratio of elastic bending modulus to surface tension. Second is elasto-capillary stretching number C sub S indicate the ratio of area stretching modulus to surface tension. So we estimated typical orders of magnitude of C sub B and C sub S by using typical values of each term of the hydrogel sheet. So we conclude that the bending energy is compatible or lower than capillarity. This means the fluid surface can unbend the gel sheet, therefore changing its mean curvature. Whereas elastic stretching energy is energetically more expensive than surface tension. Therefore, the surface tension is not able to change their Gaussian curvature that associate with the stretching energy as shown here. So we were quite intrigued this correlation and came up with a new idea of fluid interface mediated deformation and assembly of soft micro hydrogel objects. So after we quantitatively characterized the mechanical property of P9PAM, we were interested in how to design and fabricate more complex shape, especially non-Euclidean geometry, so the curved shape, by using thin hydrogel sheet. To do that, we developed the Grayscale gel lithography technique by using digital micrometer array, DMD. So DMD generate the patterned UV light to crosslinkable hydrogel. And their fast switching rate of pattern allows the higher bit of patterning. So for instance, the target metric was a hemispherical cap. Compared to 2-bit patterning, the 8-bit pattern hydrogel, so we used 256 different patterns that exhibit a hemispherical shape after swelling, so which is what we programmed. So based on elasto-capillary correlations, CB and CS, and developed grayscale lithography, we were interested in fabricating Enneper minimer surfaces as a soft particle that having zero mean curvature and negative Gaussian curvature. So by using grayscale maskless lithography, the shape of Enneper surfaces defined by this equation. So we programmed the swelling ratio omega as a function of normalized position R over uppercase R, and N determined the number of nodes. So shown here, node 3, 4, and 5. So those are 3D reconstructing images and movie, they taken by confocal fluorescent microscope. Okay, so we have successfully fabricated buckled gel surfaces with negative Gaussian curvature. So just to remind you that elasto-capillary stretching number C sub S is about 1,000, which means that elastic stretching energy is about 3 orders of magnitude larger than the surface tension. Therefore, when this 3-knot Enneper surfaces is placed at fluid interface, their buccal shape was preserved, not flattened out. So more interestingly, the fluid meniscus distorted through the undulated buccal surface. So that deformed interface profile observed by optical profilometer. So the red color indicates the positive deformation called crest, blue negative deformation called trough. So you may notice something strange because the shape has 3 crests and 3 trough initially, but at interface it showed the 6 trough rather than 3. Because to minimize the bending energy at interface, the 3-knot Enneper surface generate up and down symmetry breaking. Therefore, a negative deformation was split into 2. And the deformation amplitude was decreased almost by half. To prove that, we collaborate Chris Santangello group. Art and Chris calculated lower energy bending deformation, or called the isometric deformation, and the results show the similar fashion of deformation that we observed by experiment. Also, they calculated height profile of a combination of hexapole and dodecapole, basically a combination of 3-knot and 6-knot surfaces. And this torsion map showed the good agreement with our experimental profile as well. So using the Enneper surfaces, first we demonstrated 2-body capillary interactions. The finer assembled state corresponded exclusively to crest alignment. So the amplitude of crest is greater than trough. So the induced long-range capillary attraction between crest to the other crest should be greater than trough and trough. The next, we also studied the capillary assembly of multiple gel particles into higher order structure. So for 3-dot Ennepers, they predominantly assemble into often hexagonal structure with the cross alignment. So in the movie, you can see that 2 trimers already formed, and the cracks are facing each other and assemble into hexagonal cluster. And 4-knot gel surface form locally square lattice with the 90 angle as expected from the particle symmetry. The assembly of 5-knot particle is particularly interesting because the 5-fold symmetry particle cannot tile into 2D plane. As shown here, instead of adapting the bonding angle, the 72 degree for pentagonal symmetry, the 3 neighboring particles collapse into a local triangular configuration with the bonding angle 60 degree due to the strong capillary attraction. The key feature of shape-programmed P-type gel particle is their temperature-dependent swelling. So thereby, the capillary interactions can be switched on and off. So by increasing the temperature to around 50 Celsius, as you can see that the buccal surface were flattened at around 45 C due to the deswelling. So eliminating capillary interactions between Ennepers. By lowering temperature, their surface start to buckle and finally recover their program shape and assemble again, assemble structure with this specific directionality at room temperature. Also, we played with the 4-knot particle. They also show the thermally switchable capillary assembly. So in summary, the key message of this lecture is that surface energy of fluid is compatible to bending energy of micron-sized elastic sheet. Therefore, the surface tension can provide a new approach or new method to characterize their elastic modulus, as well as deform and assemble soft elastic objects in sub-millimeter scale in programmable way. So with that, I will close this talk by acknowledging the previous research team and my research group at UCSD. Also, I'd like to acknowledge my previous and current funding sources. Thank you for your attention.